Yeah, thank you for the introduction and for the invitation to speak here today. I'm Felippe Pavinatto. I'm a senior engineer at GE Aerospace Research Center in New York State, 3 hours west of here. So I'll be speaking to you about a program that where we collaborate with Binghamton University. So I wanted to start acknowledging the team, the GE Aerospace team, and Professor Mark Pollex's group at Binghamton. So all this are folks that worked in the program, and I'm fortunate to be the one here presenting it. This was a project funded by NextFlex through one of the project calls. So the outline of my talk will be as shown here. I will start speaking about our motivation for working on this program, then describe the approach we took for using additive electronics in this specific application, and then go over results in 5 different areas, and end with conclusions and perspectives. So in terms of motivation, I think there is an ever-increasing need for more and more complex RF systems in aerospace applications. For things like communication systems, like radars, navigation systems, for products that we have in the field out there, but also for sensing, for structural health monitoring, in the development of the systems, like monitoring properties for modeling, for instance, engine performance and things of that nature while developing those. So in order to get more and more complicated and dense RF systems, one possible way to do that, one possible solution is to use 3D packaged embedded multi-chip modules. They are attractive because you can obtain high density, as I said, of RF electronics without occupying a large area. But although those solutions are attractive, there are challenges, and those relate mostly to the manufacturing of those multi-chip module systems. They are very costly and time-consuming to fabricate, and if you think about using traditional packaging technologies from the electronics industry, those rely invariably on wafer processes, and you get different types of pad metallizations depending on where you source your materials and components from. For instance, you may get a chip with one pad finish, one pad size from one vendor, and another one that's completely different, and you have to integrate them both in our system. So that's challenging. And on top of that, everything is made for probe station testing. So when you talk about a 3D system and testing those, it's very challenging to work in that kind of setting of a probe station. All that, of course, results in complex integration. So what we proposed, our approach in this program, was to use additive electronics, and here I'm talking 3D printing of ceramics, and printed electronics techniques as micro-dispensing and aerosol gel to fabricate a non-additive multi-chip module packaged that way. So here's a little bit about, I hope you can see my pointer over there. It's very hard to point at it from here. But here you can see an illustration of an idealized packaged RF chip packaged in an alumina 3D scaffold. So we were talking about this 3D printed alumina that has a cavity where we can put a chip, and then there is also holes that we can turn into conductive vias for a multi-layer system, and conductive traces or RF transmission lines printed on the surface. So yeah, we used in this program a Lithos Serafab 3D printer based on a DLP method to fabricate this ceramic matrix. And alumina is attractive because it's a high decay, low loss, and highly thermal stable substrate. And the bulk of the work in this program